Hi guys, I'm Randall. First of all, thanks to the conference organizers for setting all of this up. It's been terrific so far. I'm sure everybody's enjoyed it. I know you guys have a choice in talks today, so thank you for flying with me. Nextdoor has a very compelling presentation as well. I think it's Jessica Care. I'm going to mispronounce that last name. So I'm going to talk about how you can take a century of weather data and shove it into MongoDB or pretty much any other database and run queries on it and all the different things that happen around that and the things you have to know about when you're dealing with large quantities of data. Hopefully we'll all learn some history, we'll learn some ops stuff, and it'll be really exciting. I practiced this 5 times for the past day, so I think I've got the timing right. I have another 2 seconds before I have to go to the next slide. All right, so this is a really creepy question, so I'm not actually going to have anybody do this. But what was the weather like on the day you were born? And I'm a firm believer that every single talk should have a live demo and code and a prop. So in lieu of the live demo, I'm going to show you a prop. This is the hard drive that the live demo was supposed to run on. Turns out taking this in a non-static bag through many airports and other things is not a good way of storing a hard drive. So I can't run the live demo. Luckily, I recorded it. So here's the recording of the live demo. And I'm going to zoom in slightly here. And I think I have to press another button to get this thing to play. Oh, great. That's great quality. Oh, well. So essentially, I'm putting in a place and time. And I'm saying, hey, Raleigh, North Carolina, and totally not my real birthday. And what it's going to do is it's going to say, what state is this date and time in? Let me query it and take that state's geometry and find all of the weather stations. It actually turns out that our server is fast enough to return all of the weather stations for the entire world, so I stopped the looking inside of a single state part. So this is all of the weather data on the day that I was born, going from whatever midnight until the next midnight. And some stations report every hour, some report every 5 minutes. We're going to learn a lot more about all of that. I know the application isn't pretty. I have no front-end skills, which if you look at my website will be patently obvious. So let's move on to something that I do have skills about. What we're going to do is we're going to segment this into sort of 3 parts. We're going to talk about the data in the schema. So where does the data come from? How do we get it? How do we parse it? How do we ingest it? And then we're going to talk about the application side of things, which is what I just showed you. And I'm going to gloss over most of that because it's kind of, I don't know, everybody writes applications. It's like this other cool stuff that's fun to talk about. And then we're going to talk about the operational concerns. And that's really exciting because I can tell you how you get to spend a ton of money with Amazon Web Services. So this is the first of a couple MongoDB interludes. This talk is about MongoDB. I'm hoping it's not going to come across as some crazy marketing nonsense. I'm not trying to be that way. I just I get paid to work on it, so it was pretty fun to spend money on this giant cluster. So anyway, what is it when I use it? MongoDB is a document data store, so that means that the smallest addressable entity in MongoDB is going to be a document. Rather than having rows and rather than having columns and rows that fill those columns, like an Excel spreadsheet, you instead have individually addressable documents that contain your data, which means you specify the keys every time and things like that. And you'll see an example of that in a little bit. The other reason I chose MongoDB for this is that it has really nice geoindexing features. So I was able to do a ton of cool stuff around that. And simple, sharded deployments. And a sharded deployment is just partitioning. So if you guys are coming from a relational database background and you've ever worked with partitioning Postgres or MySQL or something like that, rather than having to do that at your application level and at the ops level, in MongoDB it's just at the ops level. And sort of sharded deployments are a drop-in replacement for whatever other deployment you might have. The other reason I use it is that I know MongoDB pretty well. I also know Postgres pretty well, but I'm starting to know MongoDB better. So that's why I chose to do this with this database. So there's a couple of vocabulary words that we should cover. A database is still a database. A table is now a collection. Just go with it. And a row is now a BSON document. BSON is a binary representation of JSON. So I'll talk a little bit more about that. And then indexes are still indexes. Indexes are just as important as they are in normal databases, perhaps more. And then no, they're no joins. So let's talk about the data. And this is really cool. I'm going to be a little bit of a history nerd here. Bear with me, and if I get too far behind time, I'm going to skip stuff. So there's this federal entity called NOAA. They have about $6 billion in funding this year. In previous years, they've had as little as $3 billion, and when they first started, they had hundreds of millions. So they've really gotten big now, and they do all kinds of crazy cool stuff. And even smaller within NOAA is this little tiny thing called the NCDC, the National Climatic Data Center. And it started in 1934 as a tabulation unit in New Orleans, Louisiana, I think. That's the right date, yeah. And so then they branched out. They had so much work coming and tabulating all of this data that they had to go to Chattanooga, Tennessee, and San Francisco. Oh, and Kansas City is also one of the places where they did a lot of the weather tabulation. And all of this data is now stored in Asheville, North Carolina, in this giant data center. And when I say all of this data, I'm really not kidding. So the Grove Arcade building is a data center in Asheville, North Carolina now, which is really cool because I went to school 40 minutes from there, and I had no idea about this until I started researching for this presentation. So they house 150 years of weather and climate data, everything from core samples to microfiche to reports about the Hindenburg, somehow that's related to weather. And there's a ton of stuff. And when I say a ton of stuff, 13.4 petabytes of digital data. And they add another 224 gigabytes every single day. So that's big data. That's a lot of stuff. Here's the really crazy part. You can download all of it for free. So the government is just oh, yeah, we'll subsidize this. Yeah, just go ahead, download all of this data. So if you ever wanted a giant data set to play with and have a good time with, I recommend it. Oh, and in Asheville, North Carolina, they also have the World Center for Meteorology. So the Russia and China, Japan, a bunch of other places, they all collate their data and send it to Asheville, North Carolina. So yeah, Asheville, North Carolina, it's a cool place. Go visit. This is what the weather stations look like. They're mostly self-sufficient. Some of them do rely on power, depending on what sort of stuff they need to do. But they have solar panels. They're all over the country, all over the world. And they're just really powerful. They collect everything from temperature to oh, wow, that was wrong, to wind speed and humidity, just hundreds of measurements that you would never think about. I mean, I don't know if you guys can see this entire slide, but they calculate stuff like soil temperature and soil moisture and, all of this stuff. There's a lot of data, and it gets pushed all the time. So if you think about the amount of data that we used to collect in the 1930s, or even in World War II, so we collected a lot of data. And we did that so that we could make informed decisions, informed tactical decisions. But now, if you think about the amount of data that we collect, it's just tremendously more. And we're finally at the point where we can start collecting enough data to make informed decisions about climate stuff. I'm not going to be oh, climate change for this presentation, but the evidence is obvious when you go to this website. So this is what a weather datum contains, right? You have a station ID, which is hopefully geographically stationary, or for the purposes of this presentation, geographically stationary. It turns out that Germany decides to move around their stations all the time. Germans. And then you have a timestamp, you have a lat long and elevation, and then you have a lot of weather data. When I say a lot of weather data, there's a 135-page manual for parsing this stuff. I read through the entire thing. At my other talk, I had a prop, which was the 135-page printout of this manual. I didn't bring it because I don't want to carry it. There are a lot of optional sections in this data. And when I say 135-page manual, I don't mean a listing of each field. No, each field has a different way of being parsed, a different character length, maybe a different encoding. It's insane. I don't know why they did that, but apparently they have to take data from the 1890s and still store that with the data from the 2014. There are a lot of optional sections, so everything from was this tornado a fire tornado or a water tornado, to who was president. That's a real optional section. Crazy stuff. We have a lot of it. I don't really think this is big data, maybe moderately big. So I'm only dealing with 4 terabytes of data here. It's just the pure weather data. It's not any of the imagery or stuff like that. What we do have, though, is a high number of data points. We have 2.5 billion distinct data points. And that's only up until 2013, because downloading the 2014 data, they suddenly decided they were going to collect about 500 times what they were collecting in 2013, so I stopped downloading. Also, my hard drive was full. So while the number of overall documents is pretty large, the actual data size is very reasonable. So we're going to call it moderately big data, and you can quote me on Oh, and if you guys want to get this, if you just go like wget-r npn, capital N, and then it's ftp.ncdc.noaa.gov/pub/data/NOAA, and then the year. And you can just download that whole set of data. So get a big hard drive, download it all, wait for wget to mirror it, start a couple parallel processes. Who cares? It's government. They can totally support that. Although, if somebody wanted to be really awesome, you should make a BitTorrent of this data and then just serve it for everyone for free. Maybe we should do that. OK, so how does it grow? It grows pretty quickly. So I still don't know what happened back here in 1971 and 72. I think it's probably the proliferation of cheap semiconductors that made these things easier to build. If anybody does know and can tell me, I'd be really, really interested, because I spent hours trying to find this out. So what happened in the 1930s is that we knew we were going to go into World War II, so we started collecting a lot more data in order to make informed tactical decisions, and that sort of carried on. And then, it just, semiconductors. It gets cheaper and easier to calculate and store data. This is the really interesting part of this graph. This is from NCDC. Previously, this is terabytes on the side here. This is, I'm sorry, it's cut off, but it's tens of terabytes. So in 2009, they added 10 terabytes of data. In 2013, they added like 80 terabytes of data. So obviously, they're collecting a lot more data than they used to. And if you see the growth here, there's a ton of stuff that they're collecting, and they're just storing it. And I'm really interested in how they're storing that. So who else is this relevant for? Because weather's not interesting for everybody. Actually, it is, and if you don't think weather is interesting, you're boring. But who else is this relevant for? Particle physicists, because I know there are a lot of you guys in the room. So just so you know, this presentation is going to be super relevant for you guys. Stocks and high-frequency traders, yeah. Insurance companies, yeah, that's great, right? The reason it's relevant for insurance companies is that you have a lot of really random documents coming from a ton of different places, and you need to collate them into some sort of holistic, real-time customer view. And then, like, in general, people with lots of really small data points. And when I say a lot, I mean like billions and billions. I'm not quoting Carl Sagan. So, wow, that joke went flat. Nobody here is a fan of Cosmos? OK, so we're going to go through Schema Design 101. Billions and billions. So there are a couple things we care about in schema design, right? We care about performance. And performance is sort of three-axis, or three-tiered. We care about overall data ingestion performance, so the amount of time that it takes to bulk load all of this data. We care about the app-specific, which are the queries that whatever application you're designing this for will support performance, and that's mostly around indexing and query choices and caching, stuff like that. And then we care about ad hoc performance. So if you're a scientist, the ad hoc performance is the really exciting part. Unfortunately, it's also the most expensive. But so ad hoc is any sort of analytical query that you want to run. And then we care about cost. And luckily, performance and cost are pretty proportional. More money you spend, more stuff you get. And then flexibility. And one thing that I've found particularly nice about MongoDB when I was building all of this is that my flexibility didn't really change as I went from simple deployments to complicated deployments. But that's probably just because I've been using MongoDB for a long time, and other people might not find that to be true. Docs.mongodb.org or something. So this is how I'm going to measure performance, and I'll have this slide again later. What I'm going to do is I'm running a little bit behind time, so I'm just going to skip that for now. So this is what the data looks like. This is an individual datum of stuff. And obviously, it's super readable, right? Those of you from the COBOL and Fortran days definitely are huge fans of this kind of data format. I, however, think it sucks. So instead, we're going to go with this, which is a nice, pretty JSON representation of this data. And just in case you were wondering how to parse this field is the US Air Force identifier code for New York Central Park. And you wouldn't believe how long it takes to draw these little animations in Keynote. I hate this crap. Definitely use the tech in Beamer if you ever do a presentation. It's so much easier. And then this is a measurement. So you have the 21.1, which you don't know. It could be 211 degrees. You don't really know. It's just, no, it's actually 21.1. And there's really no specification for whether or not it's 211 degrees or 21.1. You just have to take realistic bounds and guess. So the quality code is something I'll talk about later, because it's not important right now. So the station So it turns out that the US Air Force has indexed all of these weather stations. They use them to make flight plans and things like that. So across most of North America and in a lot of other places in the world, there are US Air Force identifiers. I prefer those. They're shorter in terms of value size than the WBAN IDs. So I have another type of ID that I'll talk about if my thing changes. Woo. So WBAN IDs are just sort of generic weather identifiers for stations. And those are everywhere else in the world. And they're longer than the US Air Force IDs. So in almost all cases, I prefix the ID with a U and prefer the US Air Force ID. And I'll explain why later. I keep saying that, but trust me, it's all going to make sense. Or don't trust me. So for ships, we use the prefix X, and then we specify their latitude and longitude, and that's the station ID. So if a ship goes through the same place twice, that measurement still counts as coming from that particular station. Doesn't really work in the ocean. I found this out later because the ocean changes, and all kinds of things about the ocean change. And if I was doing this again, I would not have done it this way. But unfortunately, it's really hard to pay $700,000 a year for a cluster. So I'm not going to do it again. So this is Geo JSON. Has anybody seen this before? All right, yeah. So, I mean, those of you who have worked with GIS and like other geospatial systems, you know that these crazy XML formats and proprietary formats are a little bit difficult to read. Geo JSON is not difficult to read. It's all in English, but it's very verbose. But so is XML. So what is it? Bullet point. It's a rich geographical data format. So there's a spec, and then there's a great little viewer, geojson.io. Go there if you're interested in learning more. Basically, you can represent incredibly complex structures. So you think about like topographical maps and things like that, these crazy multi-dimensional polygons. You can represent that in GeoJSON. So one thing that I'd like to point out, GeoJSON in MongoDB does not support z-axis. So if you want to store elevation, you have to do that on the side. You can't put that in the coordinate pairs. Definitely ran into that problem too. So this is what an individual piece of weather information looks like. We have a ton of these sections. So air temperature is one type, and then it's a value of negative 4.9. And then the quality, so I wrote this down. So quality codes, 0 means it passed gross limit checks. And they go like 0 through 9, and they all mean different things. And they're not numerical values, so you can't, they don't get increasingly more accurate. They're just random numbers. So like 4 is suspect. Thanks a lot, NCDC, for giving me all this free data. So when it comes to schema design, we have a lot of choices, right? And I'm going to try and get through these quickly, and then we're going to get to the operational stuff, and that's going to be where you use its big number. That's so exciting. All right. So one thing that I want to clarify is that as you increase embedding, at least within MongoDB and a lot of other databases, even in like relational databases, as you sort of denormalize or normalize, forget which one it is. Wow. As you flatten your data structures, you make the logic of the data inherent in the data rather than inherent in the inherent in the schema of the data rather than in your application. So that's an important point to sort of take away from this, and I felt like I should have some sort of overarching like theme or point, whatever. So we have 100 of these optional weather codes and optional sections, right? And we have a choice of storing them inline and storing them in another collection. And really, this is just a false choice that I set up so I could talk about embedding. Obviously, you would store them inline. The way you make this decision, really, is you say, what is the cardinality of my object? If it's less than squillions, and I say squillions because trying to come up with a real number is really hard, because it depends entirely on the deployment and the database and all these different things. If your cardinality is less than squillions and it's not changing and it's only relevant to that piece of information, embed the information in the document. Don't store it in another collection or another table or anything like that. And then you will get better performance. There's some other things. So don't embed objects that change all the time. So stock guys, take note of that. And then don't grow arrays. Yeah, that covers it. So we have a couple choices around unique identifiers. We can use an object ID. I chose to go with this because it was simple, guaranteed, and unique, and also it didn't occur to me to do it this other way until later on. It costs 12 bytes plus another 5 bytes for the key. Not a big deal, unless you're dealing with 2.5 billion documents, in which case it probably is a big deal. But hey, everybody makes mistakes. This would have been perhaps a better unique identifier. The only problem with this is that in the data from 1890 to 2013, there are 130,000 duplicates. So trying to figure out a way to merge those, and as far as I'm concerned, each one was its own special little edge case, it was difficult. So I ended up not doing this. But it would have been small space savings, around 15 bytes, no, 12 bytes. And then it does make your query slightly more complex, but that's not too big of a deal. Yeah, so I think 130,000 is like 0.005% of 2.5 billion. So that's pretty good, right? Because they're collecting data from 1890 forward, only 130,000 duplicates. That's impressive. Anyway, we have another choice, field shortening. This is server bug 863. I might have that wrong, but I'll correct myself if I am, because it's in the next slide notes. So one thing that people often get wrong about field shortening is that it does not decrease the size of your indexes. I don't know why people think this, because indexes depend on values. They don't depend on the keys. It decreases readability. However, you can save 40% per document. So let's say this document is 1.2 KB, and it's very readable. But what would be like our prime candidate for shortening the field name here? We have sort of determination, quality, value. Oh, we have quality, value. If these quality and value things occur like every time, why wouldn't we just store them as Q and V? And I know you guys are saying, well, why doesn't MongoDB support field tokenization? Server 863, field tokenization. Check out that bug, it'll come soon. But if you do want to shorten the size of these right now, what you can do is you can say Q, V, and D are all their own fields, and then you leave everything else the same. That way it's still readable, and it doesn't look like this. Because I can't read that. I don't even know that AT is air temperature. So when it comes to indexes, you have, again, a couple choices. You don't want to index everything. That would be the analytics approach. But every time you index something, that's more space, it's more problems, more indexes, more problems. Just be careful with indexes. Definitely prefer sparse indexes. Geo indexes in MongoDB are sparse by default, so that you don't have to worry about that. But think about if you were searching about sky condition a lot, right? You wouldn't want to use a sky condition index on everything, because then you would have to have 2.5 million entries, or 2.5 billion entries. Instead, you would do a sparse index, and that way you would only index the documents that had sky condition. So there's this really cool feature in MongoDB 2.6 called index intersection. I don't fully understand it, and that's crazy because I did a lot of performance analysis around it. But it's cool. What will happen is you can take, for instance, the timestamp index and the station index, and you can intersect them. And instead of having to store a timestamp and a station compound index, which is when you would pre-compute all of the possible branches, you would just intersect the two existing indexes and hopefully get better performance. The issue is compound indexes tend to be more performant. And that's because we sort of prefer keeping certain things in memory. And also, the computational overhead of doing this intersection is often slower than just grabbing the stuff in the first place. And then the other really important point, which is probably why this hard drive died, actually, build your indexes after ingesting the data. It requires a lot fewer writes in order to stream all the data, and it's a lot faster, too. Imagine that. All right, I have 17 minutes, and I am not even to the operational stuff yet, so I'm going to pick up the pace. This is an overview of how the application works. The client side, you got some JavaScript, you got some Google Chrome, some pretty pictures. This slide also took forever to make. So what happens is we take the data from MongoDB, we pass it into our driver, PyMongo, and then we pass that into Python Flask, and the Python Flask, it outputs KML, which is read by the JavaScript on the client, and then sent to the Google Earth plugin. And Google Earth plugin does its magic and parses and does things. There's a really great project called Tourify about KML and JavaScript and PyMongo. Check it out. It's cool. Totally didn't write it. If you go, has anybody ever seen an aggregation query in MongoDB before? Oh, well, Jeremy. So I'm not going to explain this. Nobody really cares, right? Essentially what it's saying is, like, hey, let me get everything that's happened in the past hour that matches a quality code that isn't bad, and then return the station ID and its position and the air temperature. And then let me record that. Yeah. This is a picture. I'm going to go to the next slide, and nobody's going to notice. Ready? So this is all of the weather stations. And now I'm going to go to the next slide. Did anybody notice what changed? I highlighted New York. I couldn't find a better way of doing this. I thought about zooming in, but it's just not as powerful as this slide that doesn't change. So there's this concept of geofencing when you do your queries. And what will happen is you can take the complex polygon that represents New York, right? Which is like 2,020-some points, something like that. And because the Long Island coastline, like those guys, man, they're crazy about what's their water and what's Staten Island. Anyway, so you have this polygon, and you can actually pass this in as part of your query if you want. And you can do intersections and say, like, find me everything that's on the border of New York and, some other place. What is New York border? Pennsylvania. This thing's, give it a second. There we go. Oh, yeah, and that's how you create the index. These are all things that docs cover. I don't know. Nobody really cares. So db.states.find1, and then I have this sort of complex query going down. It says, find me what state this stuff is in. So if I take all of the state data and I say, or you can actually take all of the county data. This is available. Data.gov has a listing of not just county boundaries, but city boundaries and things like this. So you can say, oh, find me tell me what county or city or neighborhood this point is in, and let me query on it. And that's how you do that. It's pretty easy, although lots of indentation. This is the part that's fun. All right, I'm gonna take this off. All right. So we have two choices when it comes to deployments, right? We have a single server, and the single server is really great. It's like 60 grand a year or so, which seems like a lot, but wait until you see like all the cool stuff you can do. And obviously you could get it for a lot less. All of these prices that I'm quoting, by the way, are without talking with Amazon at all. It's just like blindly letting them swipe my credit card to whatever they want. And so I run the application on a C3 8X large, which is like $3 an hour, and I have an i2 8X large, which is $6 an hour. This thing has 256 gigs of RAM. I don't know why I put 251, typo. And then that is backed by 6 terabytes of SSDs. So this stuff you get for free. It's the ephemeral storage, which maybe you don't want your data on ephemeral storage, but hey, no worries. You get amazing I/O performance from these drives. Amazing. They immediately throttle you as soon as you start, bulk ingesting data. But aside from that, you get amazing performance. Thanks, Amazon. This is the other choice you have. This is a sharded cluster deployment. So it's quick MongoDB interlude. MongoDB sharded cluster, basically a drop-in replacement. You put a Mongo S in front of all the MongoDs that you want to talk to. So MongoDs are the binaries that are Mongo. And that just routes your queries for you. You can have n number of Mongo S's, so it's not atypical for people to throw them on their application server and then just treat that as like, I'm talking to localhost. My database is on localhost. And Mongo S is pretty intelligent. It does everything for you as far as routing and stuff goes. There's some crazy cool things you can do with like tag preferences and things like that, but again, nobody cares. I run these sharded, and I have 100 of them, which is really cool. If you've ever spun up 100 machines on EC2, it's just like phenomenal because you can get like HTOP going and you can like have it running in a cluster. It's awesome. It's like I've never seen that many CPUs at once on a machine. So these have 61 gigs of RAM. They're 100 gigabytes each, and they're each like $4 an hour. So that's the cost. I put it in big red numbers just because it hurts. If anybody wants to reimburse MongoDB for doing this research, that'd be great. Hi, government, NSA, whatever. Again, let's take a look at the performance breakdown. So we have bulk loading, right? We have latency. So bulk loading is that ingestion stuff, and I'm going to talk about what the optimal performance is given this deployment. And then we're going to talk about the latency and throughput for each of these queries. I want to do a point in space-time, one station for an entire year, and then the whole world at one point in time. And these seem like fairly common app-specific queries that I would want to support. There are probably a lot of others, and if this hard drive wasn't broken, I would have somebody suggest one, and then I would write it in real time, and it would be a great live demo. But no, the hard drive is broken. So then the last thing we want to support is that ad hoc, that analytical sort of stuff. So What was the warmest and coldest day? What was the average temperature across the entire world, across an entire region? Things like that. So this is a really hard graph to read, so I'm just going to tell you what it says. On the single server, I have this fancy laser pointer. On the single server, you can get about 75 inserts per second with 8 threads and a batch size of 100. And that was sort of the optimal point before either Amazon started throttling me or MongoDB started throttling behind. It's hard to tell sometimes. My margin of error on these tests was around 5%. So that's pretty good. I didn't have much variance, but I only ran them 5 or 6 times. So here's that data again. So the total amount of time to load all of this data in is about 10 hours and 20 minutes. And then documents per second, 70,000. And then the index build time, and this is kind of like the painful part, table scans, even on those SSDs, are still super slow. So if it has to page everything from the SSD back into RAM in order to build the index and then send it back out again, this like shuffling, it's just not great. And I wish there were a better way to do it. So 7 hours and 40 minutes to build that index. That's the compound index of timestamp and station. This is the sharded cluster. And I have a really cool thing to say about the sharded cluster, about 10 gigabit NICs and Amazon, and I'll talk about it in a second. So if you look around, I think it's like 225,000, something like that. The best performance I got was 144 threads running on each on each inserter that I had spun up, and then a batch size of 200. And I want to point out, this is without any sort of production management stuff that I could have done, so none of this was particularly well tuned. If I were to do this again, I would like mount my volumes better, I would set read ahead better, but I was kind of in a rush and I didn't really want to do any of that. So you could definitely get better performance, except Amazon throttles you. On 10 gigabit NICs, they throttle you. I'm probably going to get fired for saying this, but man, like if you pay for a 10 gigabit NIC, you should get that bandwidth, right? Like you should be able to push as much data as you want. But no, it turns out that even though I can peak at like 600,000 documents per second, that my average ends up only being 228,000 because they're like, you're being noisy. Stop using all the bandwidth. Whatever. You'll notice a slight difference in the time it takes to build an index on the sharded cluster. It's 5 minutes versus 7 hours and 40 minutes. You know, just a small difference, not really anything to worry about. I wonder if sarcasm comes through in YouTube videos. So I chose the shard key to be the station ID hashed, and the reason I chose that is I wanted like fairly even distribution of of stations per shard, and it was the best way I could think of doing that without doing math. This is another key takeaway from this. Back of the envelope calculations are often wrong, but probably not for the reason you expect. For instance, I did not expect Amazon to throttle me. Yeah. So let's take a query in Spacetime. And this is 1969, July 16th or something like that. And does anybody remember what happened that day? There's a picture hint. Exactly, Upgoer 5. This is Apollo 11. We go to the moon, you know, crazy, crazy cool stuff, like humans walked on the moon. It was a cool point in time. And I'm querying the station at Kennedy Space Center and trying to find out which station is at Kennedy Space Center is non-trivial. Because they have like 15 different station IDs for like the past 100 years. Jerks. Anyway. So this is what the performance is. These are milliseconds on the side. So a single point in time on the single server, you get pretty great throughput. You know, 40,000 documents per second, and that's before your performance is like significantly degraded just because of the network. So when the network pipes get full, sending data back, and then so the 99th percentile, so like the worst possible time that we got was 1.5 milliseconds, and then the average time was below a millisecond. And when you're measuring below a millisecond for networked operations, it's kind of like, really? You know, it's all sort of magic. You don't really trust those measurements, so don't trust any of that. The average time on the cluster was about the same. The worst time was less, but what did change is the throughput. And actually, the throughput was unchanged regardless of the number of MongoS's I have after 4. So I could add 20 and I could still get the same throughput, and that is again throttling. but Amazon's great. Does anybody remember what happened in 1989 and 1990? The Berlin Wall fell down. So that was a really interesting year in history. This is the history portion of this presentation. And I thought it would be really interesting to choose this year to query on. Also, our German friend made this. So this is the query. That should be self-explanatory. If not, I'm not going to explain it. The single server, worst time, 4 seconds. Not bad. The best, how many minutes? Oh my god, I'm going to run out of time. The whatever time on the single server is, yeah. And then the cluster is infinitely better. Not infinitely better. It's only like half better. Actually, the 99th percentile time on the cluster is wrong. I think I transposed the number. I couldn't get a single query on the server for an entire year to go over a second. And I tried. I was trying to like do 1990 and then do 2013 and then go back to 1991. I just couldn't get it. So the max throughput on the cluster is much higher. Max throughput on the single server is only 20 documents a second. Not that great. And the advantage of being able to do this on the cluster is that it's a targeted query. It's not a scatter-gather query. So there are two types of query patterns in partition clusters, sharded clusters. The targeted query, because I've hashed on station ID, it knows exactly who it needs to talk to and where to go and how to route that query. But this query, which is the whole world at once, is a scatter-gather query. And this is Y2K, so definitely going to be some problems here, right? This is interesting. So the cluster, under a millisecond for every query. And then there's a whole lot of data that comes back when you query the whole world at once. Like a gigabyte of data. It's pretty insane. So that's why the number of ops is a lot lower than what you saw previously, just because it takes a while to send all that stuff over a pipe. And then the single server is like, oh yeah, I can get you the entire world at one point in time. Let me just take 8 seconds. Okay, here's the part that matters, and I'm going to go really fast. This is an aggregate query for the max temperature. You could do this a couple different ways, but I did it this way. It takes 2 hours and 30 minutes on a single server. Oh, and by the way, it's in Death Valley, and it's 143 degrees. How long, and there's a prize, which is, I don't know, for the person who can guess how long it takes on the cluster.
30 seconds.
2 minutes. This guy wins, because he's the only one that talks. So 2 minutes on the cluster. Significantly better. And you can run all kinds of really cool aggregation queries, and they still take a lot less time on the sharded cluster. So if you have to support ad hoc operations and you don't want to index everything, the cluster is the way to go. If you're willing to take like 4 hours for your analysis to be done, go with the single server, because it's 60 grand a year and it's not 700 grand a year. That's a pretty easy decision. Oh, hey, I have a summary. So pros, it's cost effective, low latency for just a lot of queries. Table scans are still slow. Who's surprised by that? Cons, yeah, that's pretty much the only con. And there's another pro that I haven't listed here, and that pro is that you have 100 shards, and you get to play with them. Like, who would not want that? If you do have trouble spinning that up, and you're like, oh my god, the ops overload, what I would recommend is the MMS automation framework. So MongoDB has this crazy cool automation framework built into MMS now where you can say, hey, spin me up 100 shards using my EC2 credentials, which is giving us permission to swipe your credit card in Amazon for you. And we'll just do that, and we'll spin them up, and we'll link them. And one thing that I ran into is like, when you do 100 shards, or if you do 1,000 shards, if you do something like this, you're going to have nodes that fail. Like the initialization process is not perfect, and some of them will be slower than others. And you're going to have to contend with noisy neighbors, and I am that noisy neighbor if anybody was using this in June, so I apologize. So definitely rely on a framework for spinning these things up. Do not do it by hand or bash script. Yeah, that's my presentation. I have 30 seconds for questions. This is my cluster, and this only has like 1940 through 1990. So that's the most I can fit on a disk. Any other questions? Was it too MongoDB heavy? All right. If you guys have MongoDB questions, Jeremy and I are here for the rest of this conference, which is like 2 hours, so swing by.